Good evening, everybody. Yeah, this is going to be my third session on virtual simulations, its importance, and how it can enhance product development. So, the last two sessions we had discussed what is virtual simulation and how it's going to create an impact in the product development process. We also discussed a case study in the second session, and today, the third session, we are going to specifically focus on two different case studies. One from the oil and gas segment, and the other one from the automotive segment, specifically the two-wheeler segment. As you all know, virtual simulation is a virtual process which is created in a virtual environment using three-dimensional computer-aided design and drafting tools like SolidWorks, CATIA, Solid Edge, Pro Engineer, etc. And we also make use of styling tools like a Rhino, ISO, Elias, etc. in order to enhance the aesthetics of the product. We also make use of certain optical systems, platforms like Zimax, ANSYS Optics, etc. to enhance the physics, the lighting properties of the product. So as we all know that today we are in a revolution, industrial revolution 5, 6, where more robust applications, softwares, tools have taken charge by enhancing the products to a completely different level. So there used to be a time, the earlier 2000s, where most of the activities were performed by the product development engineer working on a specific concept, working on various concepts, interacting with his team, discussing and speculating more about the functions, the form, the shape, the characteristics, the material properties, the physics involving loads, structural loads, thermal loads, physics involving light, and the physics involving flow applications, vibrations, etc. Most of the activities carried out by the engineers on that specific product is all focused on one single characteristics, that is stability and sustainability of the product. And there is a reason that I discussed why virtual simulation is adopted all through the industry. As you know, designing and developing a product, manufacturing it, or creating a prototype, a real prototype with the specific materials are all very costly affairs. A good amount of money is invested by the company for all these prototype developments. And finally, when the product fails, the situation becomes completely miserable. So that is one of the main reasons why the earlier 90s started focusing on a platform where the complete system becomes virtual, which means that the entire product can be designed, developed, tested, and prototyped in a virtual environment where good amount of money could be saved in the process. Good amount of money. Say about 95% of the money incurred on developing a product is cut or is reduced. Similarly, the cost, the time, and various other parameters like your quality could also be maintained through the virtual simulation process. So, as I told you, like the early stages of virtual simulation tools, the engineer had to go through a completely disoriented and a completely disorganized and haphazard way of engineering processes, which means there wasn't a proper system adopted, there wasn't a proper process adopted, and everything used to be haphazard or everything used to be completely disorganized. So things used to be very difficult. Segregating few data from here, segregating few data from the other side, correlating everything, trying to understand which would be the most prominent data. The raw data are supposed to be processed, and then speculating or working on this. The end of the day, the actuals are arrived at, and based on the actuals, the engineer had to work on the design principles to design or develop this particular product. So we had tools those days which weren't intuitive, which weren't parametric enough. Good amount of effort were put by the engineers, the design engineers, based on the design principles to develop products, and eventually led to products like SolidWorks, CATIA, Unigraphics. Today we call it SolidEdge, Pro Engineer, etc. And the best part of those virtual simulation or platform was the complete product could be developed on the virtual frame. The material properties could be changed, the renderings could be seen, the mechanisms could be worked out to understand the ergonomics of the system, whether the human could handle it exactly the way it is supposed to be handled, the hindrances, the interactions, the interferences, all these parameters were virtually seen on the platform. This led to a significant change in the product development industry, on any industry, no matter it's aerospace, automotive, FMCG, white goods, any industry, there was a dramatical change in the process. The next level was thinking on the stability of the product, whether structurally the system was stable, optically the system was sustainable, thermally the system was able to sustain the temperatures, the operating temperatures, the ambient temperatures, the surrounding temperatures. whether the vibration induced on the structure was safe, was there some kind of crippling on the geometry on the material, whether there were some non-linearity on the product, whether the product was soundproof, vibration proof, shock proof. Many such complex physics were involved in every product which were designed for the aerospace applications or automotive or FMCG. The aircraft had good amount of G forces: 1.5G, 2G, 5G, 6.75G, 10G, 12.5G, etc. The G forces were heavily acting upon the aircraft structures. The structure had to be checked for flutter systems. The landing gear had to be tested. The wing had to be tested. The empennage had to be tested. The cockpit has to be tested. The cabin had to be tested for acoustics. The landing gear had to be tested for durability. So every component on that particular structure had to be checked. Likewise, the automotive systems, what happened when the vehicle had a head-on collision with a vehicle, a different vehicle of a bigger category, like a truck having a head-on collision. What happens to the passenger car? Whether the passengers within the car were able to sustain the impact, the bird impact on the aircraft engine, the rollover of a vehicle, four-wheeler, a car. What were the kind of injuries for the pedestrian as well as the passengers inside? Whether the airbag in the car deployed, whether the seat belt had provided the necessary flexibility to the passenger, or whether the passenger collapsed because of the blast in the airbags. So n amount of parameters used to be there in any scenario, in any industry vertical, and all these had to be accounted for. So we had softwares, those days, tools, general purpose finite element tools, specific purpose analysis simulation tools for multi-body dynamics, for kinematic simulations. We had tools for thermal systems like SINDA. We also had tools like ATOMS for motion simulation, multi-body dynamics. We had tools like Ricarda, which were capable of performing powertrain simulations. We had Tarsyn, which were able to do 1D and 3D coupled simulations. And we had softwares like Prescan and TNO Delft, which were capable of performing complete vehicle dynamic simulations. So the industry had been transforming drastically from 2000s to 2025. See, the last 25 years, there has been a considerably big amount of transformation in the industry. And all this happened because of the technology, the domain, the engineering processes. So even today, we work on specific tools, and these tools were backed up with excellent mathematical simulations. We have mathematical tools like MathCAD. We also had MATLAB Simulink, and these were all one-dimensional simulation tools which were capable of simulating the electronics, the mechatronics, the hydraulics, the pneumatics, etc. of a vehicle by breaking down every complex subsystems into smaller subsystems. So all complex engineering were broken down into very small entities, and the entire system were capable. I mean, very the entire system could be simulated using one-dimensional simulation where the time, the process involved were very, very less. So we can understand like how virtual simulation or digital platforms have helped companies in reducing cost and increased productivity by reduced time and shorter time or cycle to the market. So shortening the time is a very important parameter because competition used to be a very important part in any industry. First come, first serve. The company that comes with the product first will have the opportunity to launch it in the market and will also have the opportunity to sell the product and encash it and generate revenue. So every company, in some or the other way, we're working closely with the digital platform companies in order to enhance the methods in their product development or in their product life cycle. So as we all know, it starts from a concept, and the concept is created into, I mean, it's transformed into paper through sketches, 3D models, and these 3D models are virtually simulated, analyzed using tools, checked for the stability, and once the process is completed, the testings are done on the prototypes, and today we have enhanced digital manufacturing processes where products could be like created using 3D printing, 4D printing processes, and enhanced digital manufacturing services helped in correlating the actual product with the virtual product and correlate the products and arrive at the best, the optimized configuration, and then step into the production process. So the two examples that I wanted to, the case studies that I wanted to discuss was one from the oil and gas sector, that is about the induced draft fan impeller, which was almost about 1.6 meters in diameter and about close to say 1.65 tons, say 1,200, 1,300 kgs, or say 1,500 kgs. And few impellers were earlier developed by companies and which was extensively used for cooling tower purposes, where the hot air from the ground level had to be exhausted out to the top atmosphere through electrostatic precipitators. So these gases, the hot air, were a collective noxious gases from the lower atmosphere and had to be pumped out or exhausted out through the top exit. So these heavy impellers, which were rotating on a single axis, an axial ID induced draft fan impellers. So these impellers had to be developed by the company. So good amount of effort had to be put in identifying the best model, the best configuration of the blades, and the best lift or the drag coefficients, the power conversion ratios, the suitable material that could sustain very high temperatures. So a proper simulation had to be done, analysis had to be done on the structure where the system had to be analyzed in so many ways. The cyclic symmetry process, axisymmetric process, the 3D model, the surface model process, the 3D solid model process. So ultimately, it all leads to a common result. But the only discrepancy was on the uh, percentage of error in the simulation. So your 3D surface model had to be done just because the 3D solid model had to be changed every time. for various thicknesses, because here thickness used to be a very important parameter. As the thickness increases, the total weight of the induced draft fan impeller also increases. And this is a structure that had to rotate about close to 1000 RPM. A huge structure which is rotated using an external prime mover, at 1000 RPM, had to generate an enormous amount of airflow inside. So this airflow had to collect the impurities, the impure gas, and the hot air from the bottom atmosphere and send it to the top atmosphere. So this was the very purpose of designing this induced draft fan impellers. So companies like Asia Bond, Boveri, ABB, and many other companies uh, were developing impellers those days. So the process of finite element analysis eased out the pain of reducing the number of prototypes. So using the virtual simulation surface modeling, the thickness parameters could be changed, and for each thickness, we were able to arrive at results, the best deflections, the stress values, and the most optimal value had to be sent to the design department, and the remodeling of the structure were carried out in the product development center. And once the product dimensions were completed, the geometrical design, dimensioning, and tolerancing were done, and then it was sent to the casting, the production, and from where the production process happened. So all this process happened in a very, you know, lesser time, because earlier, just before the time where virtual simulations were adopted, it used to take a complete 6 months to 1 year for designing and developing a product. But today, it's really possible that multiple products, multiple such products with different configurations and designs could be generated from a single genera of the existing product. That's the beauty today, where artificial intelligence is playing a major role. So the second example that I wanted to talk about is about one of the projects that we have worked for a company, a two-wheeler segment company, TVS Motor, where we worked on a project for two-wheelers called Victor, TVS Victor, and that was in the early 2002, where the front yoke, the suspension and the front yoke system had to be optimized. So the strange problem what the company faced was every time they cast the component, there was absolutely a good results. The finishing was phenomenal. Once the casting was done, it was subjected to sandblasting and it was finally machined and everything. The process went really well till such a time that there was a slot being cut on the yoke for inserting the number plate. The moment the slot was cut, the parallaxity of the yoke was completely disturbed. So they adopted every different possible ways to maintain the center of gravity to ensure that the center of gravity of the yoke doesn't shift outward. It is always maintained within the geometry. But whatever they did, they were not able to do. So finally, we had taken that particular project, we worked on the project, and we finally understood. We worked on concepts like pre-stressing and post-stressing, and we implemented the pre-stressing and post-stressing concepts onto this, and we found out that there were certain critical spaces or places or locations called hotspots in any geometry, and those hotspots had to be perfectly maintained. We also arrived at two, three different such hotspots, and we ensured that the process that we made by alternatively filling material on the gaps that we geometrically provided, which means onto that existing model, we had dug out a lot of material from one end and increased the product, I mean the volume on the other side. So which means removing material from one region and filling it into the opposite region. So by doing so, we were able to understand that once we are able to satisfy those hotspots, the critical zones, we will be able to maintain the parallaxity. And it became a big success. It became a bigger success. So maybe, you can browse, you can go through Google, you can give for a search, I mean, you can search for the yoke assembly simulation for a motorcycle, TVS motor. You can probably find that. So likewise, there are many different cases, instances where virtual simulation has has become a boon to the company. It has helped the company in a drastical way and have saved a lot of cost. Has saved the company from the production issues or the manufacturing issues. Okay, so for today, we will conclude on this part. And the very next discussion that we can have, let's try to get into a specific domain and work on that particular domain, have a discussion on that particular domain. I hope that my sessions, I am able to make it very interactive and interesting, so that whatever I discuss, whatever I put across, is all from what I had experienced very, very long back. I'm trying to visualize it and I'm trying to speak, so that whatever I had gone through, you will be able to feel it, you will be able to visualize it. Okay, so uh, you can just subscribe this. You will be able to get a lot of videos of simulations, various simulations, dynamics, non-dynamics, and fluid slashes, computational fluid dynamics, aeroelasticity, etc. And you will also understand a specific case study and how you can relate it. Okay, this is going to be very useful for budding engineers as well as practicing engineers, product development engineers, and will be able to act as a guide. You'll be able to, you can probably refer to my videos every time you get stuck in some problem. And I also recommend that you can feel free definitely to raise questions. You can comment on this particular video. You can subscribe and you can share this video to your friends, so that they also get an opportunity to understand more about this particular product design as well as virtual simulation process. Okay. Thank you very much. And I'm happy that you are able to get benefited out of these very simple videos. I'm not making it complex, and I don't want to make it complex, just for a simple reason that I want to make this particular video as useful as possible, as simple as possible, so that every person is able to understand what exactly happens in the product development process, how virtual simulation is going to enhance. Okay, thank you very much.